Hi, I'm here today to talk about my library, Mazboot, and also highlight a couple of Scala 3 features that made this library possible. So in general, the aim of this talk to give you a way to write your validations in a boilerplate-free way. Scala 3 in general, I'd say is a very concise language, even compared to Scala 2, which was already concise compared to Java. So one of my favorite features that allows you to validate your types without almost like any validations to do from your own side is the main syntax. So as Professor Abdulradi showed in the keynote, so if you use the main annotation next to a function, then you can use it as if like as a entry point to your program. And the Scala is going to take care of validating the types. So for example, port has to be a numeric value. So if you pass 8080, it works fine. But if we pass here something that is not really a number, the user gets an error message that says exactly what was the problem. My library allows you to take this feature to the next level. So instead of using string and int, you can be more specific. You can use types like IP version 4 or port number. And those types will know exactly what the validation was, the range of a port number. So if we pass a negative number, for example, as a port, the user gets an error message that says, hey, negative is not really, doesn't make sense, it's not a port. That's nice. Main functions are not the only way you can use this library. You can validate using plethora of ways. The good old for comprehension, using either as your monad, if you like ethers, or if you are brave enough, you can also use union types. And I do have a couple of slides specifically about union types and how you can use them as if they are monads, because they usually don't have flat map implementation, but I will show how I made this possible. You can also validate using pattern matching. So this is useful if you have like a string and you're not sure if could be like IP version 4, could be loopback, could be IP version 6. You can use pattern matching to know which type, and loopback here would be of type loopback. This will be type IP version 4, and so on. The library also integrates with a couple of other libraries in the Scala ecosystem. So here's an example with cat parse. So if you have here, for example, a parser of a string, you can convert it to a parser of IP version 4, and you get your validation step on top of that parser. So in this example here, we have parsed something that's not an IP, then we got a cat parse error, fail with, and the error message comes from the library Mazboot with the exact error, the cause of the error. All right, so these are different ways to validate. There's many ways. There's only many types. There's also many types that comes with the library. But also the library is open for extension. So you can create your own types. So here is a way to create a types that describe strings that starts with 127 using a predefined validator here. You can also create new types by composing existing ones. So for example, we can take IP version 4 and we can take starts with 127 and create a localhost type, or yes, localhost. You can also use OR to combine types. So I can create IPv4 or 6, which again is the two different types combined together. There's also negate. It's not on this slide, but it exists. So as you would expect, the resulting type would validate both the left and side, so both IP version 4 and starts with 127. But also the neat thing is the compiler knows about it. So for example, here we have validated a type to be a local host. So you get a valid IPv4 and its valid starts with 127. You can take this type and put it in a variable that declares the type IPv4. It works because localhost is a IP version 4. Also, the same thing with the OR relationship. We can take localhost and put it in IPv4 or 6. Works as you would expect. All of these types, at the end of the day, you don't actually wrap string. In runtime, they are a string. It's just a compile time validation. So at runtime, it's essentially a string. So localhost is a string, also even at runtime, at compile time, it is a string. And you have access to all string methods. You can call slice, you can call whatever methods you have from string. But obviously, this is a relationship is one way, or if it's the other way, it would be wrong. It would be just normal type alias. So if you take normal string, put it in localhost, obviously this would not compile. And also IPv4, if you put it in localhost, this will not compile. All right, so this was my sales pitch. The rest of the talk, I'm going to talk about Scala 3 features. I'm going to talk how these features work. Before we start, let me first explain the meaning of the library name, Mazboot. So Mazboot is an Arabic word. I'm pronouncing it with a little bit of Egyptian accent. So it means correct, valid, sometimes perfect. You can use it in the context of sometimes food to describe that something like usually around like how much salt or how many sugar, that it has the right amount. And if you go to an Egyptian coffee shop and you decided to order a traditional coffee, you typically have to describe the sugar. You don't tell the person who's serving you the coffee how many spoons. You describe using, like, they have 4 words to describe how many sugar. So either no sugar at all, you say none, you say the Arabic word, of course, or you say like little, or in the middle, which is Mazboot. You don't then do the hand gesture, otherwise it will be silly. But yeah, you can use that to describe exactly 1 teaspoon of sugar. And this is the perfect amount. Less than this is too little, and anything other than is too much. But yeah, somehow we standardize on 1 teaspoon to be the right amount of sugar for coffee. All right, hope you learned some Egyptian slang today. Now let's talk about Scala. So let's implement our own Mazboot. Let's talk from the very beginning, back to even Scala 2, no new features yet. So we had the type aliases, which gave you a sort of just readability, really, no safety at all. So allows you a way, instead of writing int everywhere, you can use aliases to describe what you mean by int. Is it port, or is it positive number, or is it ID? Okay, works well, but at the safety department, it's not the best, because here I said our main function, we can pass an int to start, but there's no really guarantees that anybody validated that int to be a valid port number. But starting in Scala 3, we have a little bit more control. We have a keyword called opaque. So if you write opaque type, then suddenly the right-hand side of the equal gets hidden. So nobody really knows that that port number is an int, except one place, except the scope that this type was defined at. So in this example, inside model, anything inside model knows this fact. Outside it, nobody knows. So this gives us exactly what we wanted. So at the main function, you can't send port anymore because that's an int. You have to validate it. Or actually not validate it, you have to somehow construct it, create an instance of port type. Nobody really, I don't have functionality yet to allow you to get an instance of port number. So we'll have to implement it. The only place we can do such validation is inside the model. So here inside model, we define validate, that does whatever logic we want, and at the end of the day gives you an instance of port number. And by instance, I mean it's just the same thing as int, or not really instantiating an object or anything, not a wrapper, just returning the int, but the compiler checks it, like stamps it as port number. So from outside, from the main function, now we can use this function, which returns an either. So we know, we always reminded that we have to handle failures and we have to report to the user. Okay, all good. But there is one small problem we have. So main function is correct. But let's talk about the bit in the middle, the HTTP server, the code that wants to use the opaque type. The problem is it's also opaque for the users of the type. If you don't want to create ports out of int, you can't also use port number as int by default. So we lost all the methods that exist on int, so you can't compare it with other ints. You can't add one number to it. You can't do anything. So this doesn't compile because less than is not a method defined on port number. Luckily, this problem is thought of, so we do have the solution already in the language. You can expose a little bit of information. So we can expose type bounds. Before we talk about this, we have a solution without type bounds. So we can do it the same way we have done validate. We can define a function to int so that the users explicitly jump from port to int. Or if you want to make it a little bit fancy, you can use extension methods and then call port.toInt. But the solution I really like is using type bounds. So opaque types support that you can tell the user some information about the type. You can tell them the upper bound. You can tell them port number is a int. They don't know that it's exactly an int, but they know that it's a subtype of int. This int on the left side doesn't need to be the same thing as the right side. You can expose, for example, that it's a java.number. So people know they can use it as a number, but they don't know that it's int or long or whatever. So for the purpose of this library, I standardize on the upper bound is the same thing as the type. So users know its port is an int, but the compiler is not 100% sure that it's the same thing as int. So this gives us the exact functionality we want. At HTTP server, you can use port number as an int, compare it, do whatever you want. But the other side, you can't treat any int to be a port number. You have to go through the validate method. If we roll back the previous implementation where we were trying to treat pass an int directly without validation, that will not be compiled because the bound only works like one way. Port is an int, not the other way around. Okay, so this trick, this opaque types and the bounds is really the core of the library. Let's take this idea and make it a bit more generic and reusable so we can define hundreds of types without really writing that much of a code. So we will define a interface, a trait, that contains the following. It will contain the opaque type. That trait is parameterized on the row type. So the row is int or string, anything that already exists in the Scala standard library. Your opaque type would be something like IP, host number, and so on. So we expose that is a row. This is the only information we expose, and the right-hand side is hidden because this is opaque type. There is an abstract method that we will have to define for a couple of the validations we define in the library. So given a row value, so given an int or a string, you should somehow validate it, then at the end of the day call If it's successful, if it matches your validation, call the onSuccess. If it doesn't match, call the onError, and both those two mappers functions should return an A at the end of the day, and this is what you return. This is what the library returns to the user. This is the low-level function, validation function. Then on top of that, we have validate either, validate try, option, and your favorite monad. On top of this layer, we have a couple of bit more easier to use classes. So most of our use cases, the validations are pretty much a predicate, like number that has to be greater than 0, or string that has to match regex. So I've created the from predicate as well on top of that. Takes the function that gives you true and false, and also you have to pass an error message, or like a function that creates error messages. Then it implements the validate with for us. So it's an if else. If the matches the predicate, return, call the onSuccess, otherwise call the failure. One of the first hurdles that I have hit when we're working with opaque types is that you don't inherit. So here we have inherited validation. We have access to valid. We can call valid, but we don't see the right-hand side. So this validate with here actually doesn't, the implementation doesn't work, because this scope here doesn't know that row is a valid. This implementation should have been defined here. So this was the first hurdle. You can't extend, like, yeah, there is no protected like feature. It's all like private, like on the right-hand side is private by default. There's no way you can say, oh, show it to library classes that extend. However, I did find a way around this problem. So the trick is to override the type. So pretty much the same line, copy paste, but add override on the left. This suddenly, haha, now you know that valid is row in this scope as well. So now it compiles. So first hurdle solved. Then obviously I don't want the users to keep writing override opaque types if they want to create their own predicates. So I have defined like a layer on top of that where, so people should either extend from predicate directly, then either they don't have to do the override. So nobody really should extend validation directly. Otherwise you'll have to write override yourself, and that doesn't look good. So either extend from predicate or extend a bit more useful layer on the top. So for strings, I have defined things like, oh, matches regex, or starts with a string, or trimmed, for example. Or for numbers, it's greater than 0, or within the range of like port and so on. So ideally, you should your types, like port, for example, should probably use one of those matchers or one of those validators that come in the library. All right, so to define a type, we have two ways. There, either you extend as an object. So here we have defined a validator for port numbers, or the syntax I like a little bit more is using val. So val port number equal an instance of inRange. They are essentially the same thing, but the val gives you more power, some extra power compared to object. Yeah, I will talk about it. It allows the and or combinator, which you can't do with objects. All right, so let's start using what we have built already in a little example. So we have our port number, and we have our IPv4. So the actual port number type is the valid alias that's inside the port number object. Remember, opaque type valid. So you have to refer to that .valid, or as for convenience, I've set that as a convention. So every time you create a type validator, create an alias that points to the .valid that's inside it. And all the libraries all the types that comes from the library already does this trick, and they have the type alias. So now it looks like it's a normal type You don't have to type .valid yourself. So port is just a port number. Yeah, then we can do our usual code. It's an is a int, so you can use it here as you'd expect. Okay, so let's talk about the other side. Now, we have talked about using the port number. Let's talk about creating the port number or validating an int to be a port number. So far, we have provided only the validate either functionality. I didn't yet implement the functionality that makes it work with Scala functions, the main functions annotation. So if we try to do that, we get an error message that pretty much is very helpful, pretty much tell you what exactly you want to do. So it tells you no implicit argument for type command line parser.from string of port number. So immediately from the error message, we know that seems it works via type classes, which is very easy to extend and define for your own custom types as well. So let's define one for port numbers, or actually let's define one for any type that's inside the library. So it automatically has instance without any code, without any custom code from the user side. So let's go back to our validation class. So right after validate either, we are start to write the type class instance. So this is a Scala 3 code. Now we write given and using. I will translate to Scala 2 in this, in case this is a little bit more familiar to you. So we are creating a from string instance of valid, given that we have, or assuming that we have an instance of from string for whatever row type is. So in the case of port number, we want a from string for the type int, and this already exists in the library. Exists in Scala itself. So we know it's there. So we call the underlying parser parse first. So from string, we get our row type, the int or the string. Then we can validate on top of that. And in case of failures, we throw exception, which exactly the contract that from string expects. So that's, yeah, you have to throw exception. You don't return it either. Now, let's see if this works or not. This does work. So now if we call our program and we pass like -1 as an input, you get an error message that nicely tells the user. So the right-hand side is that's error message that's generated from the library. All right. There's also multiple other ways to validate. So I've talked about validating by pattern matching. Let's see how we can implement this in the library as well. This is much easier, really, compared to the previous ones. So this is using the good old unapply method. So we'll go to the companion object, the validation class, and we define unapply, takes the row type, the int or the string, then gives you an option of the valid type. Validate with some.apply or none.apply. One word of caution, I have to tell you, whether you're working with my library or you are working with opaque types in general, don't validate by type. Like, don't try loopback : the type loopback. This doesn't work because there's no information at runtime that says if that number is if that's a normal string or that has been validated. So the compiler is going to warn you if you try to write like by the is instance of like : then the type, automatically you will get a warning from the compiler. I think this should be an error, not a warning, because your code is probably wrong. But yeah, this is the way that the library provides you. If you want to pattern match, use the unapply method. Don't do the : and write the type. All right, we have finished now multiple implementation of multiple ways of validating types. Let's talk about the cool feature of combining types. So using the and the or combinators. So the example was something like that. We have a type that strings that start with 127. Then we want to build a loopback type that is both IPv4 and start with 127. So let's define this and function. So let's start first by implementing the easy logic, the validation bit. The validation, so far in this slide, there is nothing that tells the compiler that localhost is at IP version 4, but we have done it in the runtime. We know that the validation has to be the validation from the left, this .p and that .p. And the error message will also be composing the two error message together. Now, the interesting part is to how to also tell the compiler that this AND relationship exists. So let's try using this trick. So I've tried to override the type valid. So when I'm now instantiating an anonymous class from predicate, and I'm specifying that the valid type, I've dropped opaque anymore. It's not opaque, just like a normal type alias. And the value I'm using union type, sorry, is it not union, the other way around. So this is like with keyword in Scala. But yeah, this is the new, in Scala 3, you can't, like it's deprecated, don't use with, you have to use and. So we have defined here that our type is this dot valid and that dot valid. This seems like it should work, but actually it doesn't, unfortunately. Still, our implementation, the compiler doesn't know that loopback is a IPv4. It doesn't know this information at compile time. What's the reason? So if you have worked with type level programming or have worked with shapeless before, you probably know that the compiler tends to forget about type members. It prefers information to be captured in the type args instead. There is a solution, shapeless. I found it multiple times in shapeless code base, is to define an alias for your type, usually called the aux or the auxiliary type, that uses refinement type syntax. So you can define this type alias for from predicate, but you also put a condition that the type member inside from predicate has to match the type V. So this what essentially gives us is the ability of lifting that type member to be part of the signature, part of the type args. So from now on, we'll start as much as possible. If you want to do any like and or any type level computation, we will express our output in terms of this AUX type. Then we create also a constructor that does the same thing, creates a new, like a anonymous class on the fly, overrides the type valid to be V. And the most important thing here at the type signature, it ascribes it to be specifically AUX row and V. So the type system would not have the chance to forget about the type member. It's there, it's captured in the type signature. Now let's rewrite our AND function using the AUX constructor, and returns AUX, the row type, and the V type here is this dot valid and that dot valid. This time works. So this time the compiler doesn't forget this relationship and retains it, and now it works as you'd expect. So this is how AND works. Or as well is something very similar to that. So we're using union types to describe this dot valid or that dot valid. And yeah, they also work on multiple levels as well. So here, loopback had a relationship with IPv4 using AND, and has a relationship to IPv4 or 6 using the OR combinator. So they all compose with each other nicely. So you can have them as nested as you want, ands and ors and ands and ors. All right, now let's talk about the, I'll say one of the most interesting hacks I have done on top of union types is to make union types work with for comprehension and work as if they are monads. They are usually not monads. So normally, if you would write this code, that will not compile because the compiler really doesn't know that one of these types is supposed to be the bad case or supposed to be the left side. There's no flat map defined. There's no any methods defined on union types. All right, let's start allowing this functionality. Let's allow for comprehension. So the first trick that came to my mind is to define, let's start first defining a validate function here, to change it so that it returns, instead of either, it returns a string. Sorry, not change it, it's another function just dedicated for union types. So return on the left, the string as error message, and on the right as valid. I've already did a couple of mistakes here. My first mistake is just pronouncing the word on the left and on the right. There's no such thing as left and right with union types because string or valid is the same thing as valid or string. There is no left and right. And definitely there is no runtime information that can tell the compiler whether this is a left side of the union or this is A or this is B, which one of these. So the code I've written is actually not that bad here, but it could be really dangerous. So if you have a type that IPv4 that is an instance of a string, you'd get a type. So without this ascription, you could actually get a type that's not that bad. You get something that say it's a string or IPv4. So you still know like there's two types here, but the problem is that IPv4 is an instance of a string and the error message is also an instance of a string. So the compiler gives you the capability of actually treating as both of them as a string at the end of the day. You can call methods on string and then suddenly you have forgot your validation. You have forgot to handle the error. You start calling like slice or whatever, then suddenly, boom, there is a big problem in your logic. So never trust, the lesson from this slide is never trust generics and union types. However, we can do a little bit of tricks to give us some confidence. Like we can use generics, but with some tricks. So one of the tricks is, let's make sure that one of the sides is a type that we control and is not a type that the user has access to very easily. So it's not a string, not an int, not anything. So we define case class error that's inside validation. So it's a different class for port number, different class for IPv4, different class for IPv4-6. Yeah, is going to be all different class. And this is the error side, the type that represents an error. So we do have some sort of runtime information. So we can ask if the type is instance of error at runtime. So we can know if it's failure, or otherwise we know it must be the valid, must be the other type. So let's use this trick to try to implement flat map, so that we can use it with for comprehensions. Yeah, so far I didn't implement flat map yet, but let's start implementing it. So here's how flat map looks like. So we have defined an extension method inside validation that takes error or valid, then defines flat map and map. Flat map would be function that takes f, takes the valid type and converts this to either an error or a different type A. So the trick here is we only what you only call unapply, or only check the type of the error, only the side of the union type that we control. So check, is this an error? If it's an error, then we propagate the error as is. We short circuit the flat map. If it's not, then we know for sure it's the other side. It's valid. So I can cast it to valid with 100% safety. I know is not going to be an error. You might still get a little bit of warning here from the compiler, is a bit unhappy with you calling match on value, but you can call, instead of doing pattern matching, you can call value dot is instance of error, then as instance of. This kind of, this is exactly what we are doing and doesn't have any warnings associated with it. One interesting thing in union, when treating union types as if they are monads, is that both flat map and map becomes exactly the same implementation. Actually, like map is sort of a special case of flat map. There's no boxing really, nothing to flatten. It's already, the type is directly as is, so it's the copy paste of the implementation. Actually, in the library, both flat map and map they both call fold. All right, so let's use this. So it kind of works. So you can call .map. So in this example, I've deliberately called .map and I have done operation that returns an int. So here, up until here, I don't have an error or port anymore. I have an error or int, which again, the extension method here doesn't provide functionality for error and int, only or valid. So you can't call .map again. So you call map once, but then once the side is not valid, the method doesn't exist. So you can't call map again, which is a bit annoying for the users of the library. You probably want to use my types in a for comprehension, and you want to keep continuing mapping and doing more computation, more transformations on the type. So I have done a trick. I've took that extension method outside validation, and actually I took it outside the library completely. I'll talk about it at the end. So I have done a super type validation error, extends exception, because why not? It's useful to throw exception if you want to. Then I define the validation types on, so instead of valid, I made that a generic type A. So on any validation error or anything, you have flat map, you have map, and you have get or throw, and you have also the same functionality as before. Yeah, so this works with valid types inside the library, and also works if you call .map or the flat map and you take it out of the library and use other normal Scala libraries. Yeah, then that base class, now all the errors inside the validation extend from this base class to get this functionality. And now it works. So here we have done for comprehension. We ended up with this type that is error or string, yet it still has the functionality. You can call get or throw or call map again. I found this functionality really useful that I took it completely out of the library to its own library. It's called Happy Path. And now it works as the follows. All you need to do is, if your error type extends exception, you just type derives error case. And this automatically gives you all the methods like get or throw, gives you flat map, and so on. You can use it with like the users of that type. They don't have to import anything. Those methods are in the scope of this validation error or anything. If it's part of the union type, then suddenly you have flat map, and flat map is designed so that this is the error case in the union type. Also, there's few different flavors to error case. There is also unhappy case if you don't extend exception. So this one it works like an either. So it doesn't have get or throw, but it has other things like I don't know what you have on either. You have for all, for each, and so on. You also, if you don't want all the methods, like you don't want it to behave like an either, but you just want the for comprehension, you want flat map, map, and filter, you can use this is the lightweight version, just gives you those methods for comprehensions. Finally, this is the last slide before I start wrapping up, is how to extend this library, how to define integration with other libraries. So there is a type class called of, validation of, that allows you to jump. So here at the bottom line, it allows you to jump from a valid type to the actual code that validates it. And also you can get the type, if you want to do type level programming, you can know what's the row type of it. So from port number, I can get programmatically how I validate it, and what's, like, is it backed by a string, or is it backed by an int, or what's the runtime type. The implementation looks like something like this. Here's the type class, to information, type alias, and a reference to the validation. And this automatically, this instance of this type class is part of the trait, the validation trait. So any type in the library, or even types that you define yourself in your own code base, will have this instance defined, and just you can summon validation of and jump from the type to the validator automatically. So let's give you an example how to use it. So I've used it when I was building an integration with a library called Sirius. So Sirius is a library that allows you to do config. You can load config and you can validate it as well. So it works with type classes. So if your type has an instance of config decoder string to your type, so string to port number, for example, then Sirius will work. If not, then yeah, Sirius can't work with your custom types. The way I've defined it, so first step, I ask the compiler, okay, tell me what is the row type of valid. So using validation.of valid, it will go look for the instance implementation of port number, which exists for any type in the library, or your own custom types as well. Then the next step is to translate. So now we want port number dot row, which the type system can do this type level computation and can figure out, it's backed by an int. Now what we want to do actually is look for config decoder from a string to an int, which I think this already exists in Sirius itself. So this derivation works. I've omitted the implementation because it's not really that important. I just want to highlight the type level computation capabilities. All right, I'm almost done. So to summarize, we have talked about a couple of Scala 3 features, the main syntax, opaque type, union types. I've talked about Mazboot and a couple of features that it allows you. So we have learned that it's all really around new types. So it allows you to do refinement types and new types that hybrid together, and it's all built on top of opaque types. And this is how it tries to reduce the allocation in your code base. So by representing your validations or your validated types as opaque aliases, and as an experimental feature as well, you can do your for comprehensions using union types, not either. So you don't instantiate an either every single time. You just go through the happy path, just your valid types. In case if there's an error, we'll instantiate the error class for you. It comes with types out of the box and also allows you to create your own custom types or combine things using and or. I've also mentioned that there's some functionality around using union types as monads has been extracted to its own library. It's really just, this library is literally one file. So it's useful if you have a library or you have a large code base, you just derive that type class with your error cases and just forget about it. People will be able to use it with for comprehension without really knowing that this happy path thing exists at all. All right, here are some links. So here's the link to Mazboot. Here's the link to happy path. And this is a link to Refined. It's a library that I have been using and I'm still using that gives me the same tools I've been building with Mazboot, allows me to refine ints and do validations on the type. I'm not really sure if it will be ported to Scala 3 or not, but if you are, so Mazboot, by the way, doesn't work on Scala 2, it's only Scala 3. So if you want this functionality on Scala 2, then definitely use Refined. I use it myself. This was an introduction to boilerplate validation using Mazboot. I am Tamer Abdulradi, and this is my Twitter. Feel free to ask me on Twitter or here in the questions as well. Thank you.
Tamer, thank you so much for that talk. And I think we have a few questions, so let's get into it. All right. Our first question is this a direct competitor to Refined?
I think so, yes. So I'm not a maintainer of Refined. I've contributed a couple of integrations to Refined with other libraries. To be honest, I don't know if it's going to be ported to Scala 3 or not. Maybe yes, maybe no. But also this library works a little bit different than Refined, that it gives you new types capabilities. So Refined just gives you the refinement types. It doesn't give you the new types capabilities. My library is hybrid, so it's not direct competitor, but definitely if you use my library, then you will not be using Refined.
Got it. That makes sense. All right. Next question is it possible to customize error messages for built-in types? That is to have invalid IP in IPv4 instead of regx error.
You can if you have the time. So IPv4, this one-liner that says IPv4 is extends matches with the regex. You can override there's a method called format error message. If you want to define an error message for every single type, yes, but I don't have this kind of time.
Got it. All right. Next question, and I think this is our last one. Do you already have a plan to implement integration with JSON libraries like Circe and database libraries like Doobie?
Yes, I have a plan. So I really want. So I use Circe. So at the moment, I didn't use this. I didn't use Circe with the Scala 3 yet. But I think once I do it, obviously I'll start integrating with my library. Yes.
Awesome. Well, I think that's it for our questions. So thank you again so much for your talk today, and enjoy the rest of ScalaCon.
Cool. Thank you. Bye.